Okay. In section 3, we need to talk about difference equation of Z transform. Okay, this is important because everything is related to discrete time systems is built based on the difference equations. Okay, firstly, must consider that LTI system, especially for the discrete one, like x k the index of the discrete systems. Okay, and so a1 x k minus 1 plus a2 x k minus 2. Okay, and blah blah blah, and an x k minus n can be given for the system equation. And also we can write that the input value just like this one, b0 dot uk plus b1 uk minus 1 plus blah blah blah, and bn times u k minus n. Okay, and so then we can take Z transform just like this one, xz plus a1, this is the k minus 1, which means that we need to add the z over minus 1, xz plus a2 z over minus 2 times xz plus blah blah blah, and an times z minus n xz, which is equal to the what? b0 uz plus b1 z minus 1 uz plus blah blah blah, bn uz times z over minus n. Okay, in the collection form we can collect all the terms of the xz just like this one, xz 1 plus a1 z over minus 1 a2 z over minus 2 plus an z over minus n. Okay, and also we can equalize the whole term uz b0 plus b1 z over minus 1 blah blah blah, and bn z over minus n. Okay, and so if this is the case, we can write the whole equation in terms of the pulse transfer function, xz divided by uz. This is the ratio of the for a given input value in the discrete time, how much we get the xz in here. Okay, and so we can write just like this one, b0 plus b1 z over minus 1 blah blah blah, and bn z over minus n. Okay, and also we have denominator with the terms of the 1 plus a1 z over minus 1 blah blah blah, and an z over minus n. Okay, this is the R transfer function in the discrete time domain. Okay, so but we note that we have always continuous system in real life application. Okay, besides we can only utilize the digital signals in the microcontrollers, which means that we need to apply these rules on the continuous system just like this one, and then we should discretize the whole the continuous system, and then we will transform whole these discrete equations into the what? Into the Z transform form, okay, or the pulse transfer function. This is important, okay. So how can we do that in this domain? For example, the section 4 is directly related to the what? The continuous to discrete operation, okay. This is important because in the real life we have only continuous system, and so we need to write a continuous equation, not the discrete one, okay. So firstly, in order to discretize the system, we should use forward, backward, or centered equations by this is summarized as the Euler discretization in the literature, okay. And so in order to do that, we need to split the R area just like this one, okay. And so we can write the whole the derivative terms. The first derivative can be simplified as the x plus h like the what? The k, the index or the minimum index in here, just like this one. This is the forward, okay. And also we can take the backward difference equation in here. Fx is the first term, and so this is the backward minus h should be given in here, just like this one is the backward, okay. And also we have utilized the what? The centered equation. Fx plus h minus fx minus h divided by h, okay. This is the centered, okay. And also we can expand the whole terms in the second derivative term, just like this one. Fx plus 2h, we should utilize the what? We should forward the two terms in here, just like this one. 2 times fh x plus h minus fx should be given divided by the h square, okay. Or in the backward notation we have the what? The fx minus 2fx h plus fx 2h h square, okay. And also we can expand the r terms in the what? In the centered form. Fx plus h minus 2fx plus fx minus h divided by h square, okay. And so if you have a first order or the second order system, and then we can discretize whole the system using the what? Using this equation. In order to what? In order to implement our algorithm in the digital formats or the digital domain, such as the microcontroller or the programming language, can be used based on this information, not the continuous one, because the continuous equation should be solved by using analytical solutions, okay. And so how can we write an example about that? Firstly, just consider that we have the example in here. Consider the system. Like x dot equals to minus a times x plus b u with a greater than 0, okay. And so firstly, in order to analyze this system, we need to take the Laplace transformation. Laplace transform gives us the what, the s x s, which is equal to what, the a times x s plus b times u s. Okay, and so in this domain, in the continuous formats, we have the transfer function just like this one, b divided by s plus a. Okay. If we want to solve this equation, and then we can use this transfer function in the continuous domain. Okay, but in the discrete domain, for applying the z transform, we use the what, the forward difference equation, or backward, or centered in here, because we cannot take the direct implementation on this data, because this is the continuous equation, not the discrete one. Okay, and so if we use the forward difference equation, x dot yield us to what, x k plus 1 minus x k divided by dt. This is the first order difference equation, and then minus a times x k plus b times u k must be written in here. Okay, and then we reorganize the whole equation, just taking the xk at the right hand side, which is yields to the what, the xk plus 1, which is equal to the xk plus dt times minus a xk plus b u k. Okay, and so xk plus 1, which is equal to the what, the xk 1 minus dt a plus b dt u k. Okay, and so that's all. This is our last equation for the what, for the implementation of the z transform. We can apply this equation to the what, to the z transform, not this one. Okay, just remember that this is important. And so now we can take the z transform of this equation just like this one, z xz, because this is the x k plus 1 in this in here, and so z over 1 should be given in here, and also we have the xz 1 dt a plus b dt u z. Okay, and after that we can take this term at the left hand side, and so the xz, which is equals to the what, the z minus 1 dt a, which is equal to the b dt u z. Okay, this is the last form of the r equation, and then we can collect the whole equation in terms of the pulse transfer function xz divided by uz, and so this is equal to the what, the b dt divided by z minus 1 dt times a. Okay, these are the transfer function, but we have the additional term in here, dt, sampling period. This is just like the transfer function in the continuous domain, but if we utilize the discrete domain, and so we can add the what, the dt, sampling period, to this equation, and so this sampling period directly affects on the what, the stability of this system. Just remember that. If we take too high this value, and so this transfer function may be unstable. But how can we make the either the system is stable or not, or how can we decide that our system is stable or not in this case? Firstly, stability criteria can be given in here, just like this one. Just remember that in the continuous domain, we need to poles at the left hand side of the S domain, which means that all the roots should be negative or smaller than 0. Okay, and so if we have the hz just like this one, yz, xz, which is equals to the what? The b0, b1, z minus 1, and bm, z over minus m, and 1 plus a1, z minus 1, and an, z minus n. Okay, and so in order to check the stability of the R digital domain, we need to check the denominator of this equation, which is the characteristic equation in the discrete domain. Okay, and so if we have this condition, and then 1 plus a1, z over minus 1, and an, z over minus n should be equals to 0. And so what is the condition? The condition is that the roots, the absolute roots, must be contained in the 1. Okay, and so if we have any root in the digital domain which is smaller than 1, we can say that our system is 0 or stable. Okay, for example, in this case we have this condition, and then we need to take that the 1 minus plus dt times a must always contained in the what? In the 1 or smaller than 1 for the stability rule. Okay, for example, if we have this equation, and then we can check the roots in here. For example, the z must be smaller than the 2 times dt a. Okay, this is the conditions. Or the minus 1, this is the 1, the minus 1, z1 dt a 1. This is the first condition for the R system. The another conditions comes from these equations, just like this one. If we have this equation, dt a must be smaller than z, or the roots of the z. Okay, these are the conditions, because if we take this one value to the another terms, and then we have the another terms in here with the terms of the minus dt times a divided by smaller than z root, and then we can say that the R system is the stable. Okay, and so that's all for this lesson. And so in the next session we will solve some equations or some problems in order to make you to prepare for the exams, and we will review our lesson in the next session. Okay, but just remember that we need to check all the time the stability for the digital signal processing. For example, designing the low pass filter, high pass filter in the digital domain, or designing the discrete controller should be tested with the stability rule. Okay, and so another term, the important term, is that the sampling period is utmost important in the digital signal domain. Okay, and also we need to say that if we have any continuous system, we should utilize the forward difference equation to convert this continuous one to the discrete one. Okay, and after that we can apply the Z transform to this discrete equation or the discrete system equation. Okay.